So there are times when algorithms we design unintentionally leak secret information. Okay, so today we're going to look at the timing attack. And this code excerpt is from Mr. Colin O'Flynn, and I found it really interesting and I'm going to share it with you guys. So we have a function which is called does password match, and it takes its input as password. And we have the correct password to be 1234. And so essentially it's going to run through the password, input password, and check whether its corresponding element is the same as the correct password. And if it's not, it exits, and then otherwise it waits for 50 milliseconds, and then at the end it returns true if it's all correct. So for example, if we pass in, say, 1089, 1 and 1 is going to compare with this one, 1 is going to compare with this one, and then we say that it's correct, it jumps, and then it waits 50 milliseconds, then it goes to the next value, which is 0, and 0 compared to 2 is not equal, so it returns false. Okay, so what exactly is a timing attack about? So as I said early on, our correct password is 1234 1089. When we compare 1 and 1, that is this one and this one, it's correct, so we wait 50 milliseconds. And when we compare the 0 and 2, we see that it's false, it's not correct, so it's false, it returns quickly. And so our delay time is 50 milliseconds. In another example, say we have 1246. 1 and 1 is going to compare. This one and then the one from the correct password is going to compare. It's correct, we wait 50 milliseconds. 2 is going to compare against the 2, it's correct, 50 milliseconds. Then it's going to compare the 4 and the 3. This 4 and then the 3 from the correct password. They are not correct, so it returns false. Over here, we see that the elapsed delay time is what? 100 milliseconds. And then for the case where it's the input is actually the correct password, we have 1, 2, 3, 4. It compares 1 and 1, which waits for 50 milliseconds, 2 and 2, 50, 3 and 3, 50, 4 and 4, 50. And then we see that the elapsed delay is actually 200 milliseconds. So an attacker who has an idea of the implemented algorithm and then the way it's structured can actually measure the execution time to extract the information we need. Okay, so for example, if we are the attacker and we have an idea that, say, the password is only numbers with only a 4-digit number, essentially we can generate all possibilities for this 4-digit number. That is to say, we can generate all 10,000 possibilities. So we know that there are 4 literal spaces slots where the numbers can go into. The numbers are 0 to 9, and 0 to 9 there are 10 of them. So that means we have 10 possibilities here, 10 possibilities here, 10 possibilities here, 10 possibilities here. So we multiply them together, we have 10,000. But in my demonstration, I'm just going to use without repetitions, okay? So that's nearly my choice, okay? Because of my computer, please have mercy on it. So we're going to have 10 possibilities, and then because there are no repetitions, that means we're going to have to take one number out. Then we have 9 possibilities. Then the next one is going to be 8. Then the next one is going to be 7. We multiply these together, and we see that we have 5,040. Okay, so let me generate all these possibilities. Let's look at the brute force, okay, to generate all these possibilities. So essentially, there's the code for generating the possibilities. We see that the permutations are of length 4 without repetitions, okay, and it's going to write it to this path, okay. So we have Python3 brute force. It's written, it's there. Then let's see the brute number. Then all 5,040 possibilities will be written, okay. So yeah, but because I'm just doing it for demonstration purposes, I'd like to take some numbers out. Well, firstly, let me just show you guys something. So we can do WC, and then we see that there are actually 5,040 of them, okay. But I'm just going to take some of them out. So when we graph it, we can actually see it quite clearly. Okay, so I'm taking around the actual correct password. Let me take up to, say, okay, maybe I don't know, maybe somewhere here. Okay, this should suffice. I'm deleting the rest, and then okay, and then I'm saving it again. Okay, so when we do it again, let's see. Okay, there are 39 of them. Okay, and so now we can actually look at our Python script, which is the timing example.py. Okay, so this is essentially the pseudo script, pseudo pass code we've already looked at, and its corresponding NASM looks like this. Okay, and in the NASM I actually tweaked it a little with the command. It's going to take a command line argument, the same over here, and then it prints out an error if it's not equal to, and then over here we have the correct password and the PSWDI, where it's going to check whether the two are equal or not. Otherwise it delays. If they are equal, it delays for 50 milliseconds. And we now see that the sleep actually takes in, for the RAX, it actually takes in 35. And then we have the delay, which is defined over here. And then also we're going to sort out the RSI. This is actually seen from the R Chapman. We see that 35 goes into the RAX, then the RDI takes in the struct time spec, and the RSI takes in the time spec RMTP. And when I scroll up, you see that the column names are actually the RAX, RDI, and then the RSI. Okay, so it's actually nothing new. We've already seen most of these, and yeah, okay, so is going to take in the number of possibilities, the possibilities, and then we're going to have to write the possibility against the time it took to compute it. And then this is actually written in a script called the timing underscore sh.sh. Okay, so we see here that I have the brute number.txt, which now contains 31 possibilities because I'm using this for demonstration purposes. And I'm going to read each line, and I'm going to pass each line as a parameter to our Python script, and then it's going to calculate the average. It's going to do the computation 5 times. That is, it's going to read the times 5 times, and then it's going to take out the average, and then receive. So what I mean is this. So when I try to do timing sh.sh, we're going to see that I also wrote the same script for the timing sh.asm, the assembly file also. So let's wait for this one. And so essentially, as we said early on, because when over here, look at this example, it gets to the second point and it's not the same as 2. It's not the same as the correct password. It exits quickly. And then we see that when it's actually 2 and the third one is wrong, then the delay time is a little bit higher. And then for when it's all correct, we see that the delay time is actually much, much higher. Okay, and then it reduces again and it goes down and down and down. It goes downhill again. And so let's do the same thing for the assembly script. Okay, of course, assembly is much faster than Python. And then we see that because it's left 50 seconds, it's 50 seconds for over here. And the same thing for the right hand side. We also see that when it's exits early, we see that the timing is lower. That's the delay seconds. And then when it's a little higher, when 2 of them are actually correct, the timing is a little higher. Then our actual timing, which is 1, 2, 3, 4, we see that it's the most high. It is the highest, not most highest. It is the highest, and then it decreases again and again and again and again and again and again. Okay, so all of these we can actually write them to a file. Then we can graph it so it looks much nicer. Okay, so I have the timing, the same script as above, and I'm just going to write it to what I term as the time.txt. Okay, so it should. Okay, so the prompt has returned back to us. So I also have the script, which is the draw graph. Okay, so it essentially is going to draw our graph for us. It's going to just do is going to place in the x-axis. For the x-axis are going to be the possibilities, and then the y-axis is going to be the time. Okay, so we have this, and then we draw our graph .py. Then we see, so we actually do see that 1, 2, 3, 4 has the highest, time and delay as compared to the others. The reason why I added the time and delay is to mimic, say, some heavy computation, okay, because 1, 2, 3, 4 is actually quite short, and it's going to actually affect the timing signal. Okay, so I added the timing delay, which is a 50 milliseconds, so we can actually see the disparity or the differences within. Okay, so over here now we see 1, 2, 3, 4 being the highest, and yes, of course, that's what our point. So you see, after 1, 2, 3, 4 is the highest, and then we actually do the others, they tend to decrease again. So it's going to look like a bell curve in the normal distribution. So it's going to go something like this. Okay, yeah. So how then can we resolve this or try to ameliorate this situation? Okay, so that's where another point comes in, where instead of implementing it this way, we can try to do a constant time password comparison. Okay, actually constant time is only theoretically possible. The reason being that there could also be like there's compiler optimizations which can actually affect the timing signal for the code. There is also context switching. There is also Python in itself has overhead and all that. So what I mean by constant time over here is they are similar. Okay, it's not like perfect, but it's near perfect. Okay, so for example, this is a function, and in the function, of course, we're going to check the two lengths whether they are the same, and if they are not the same, we exit. Okay, but of course, in our example, our possibilities are all of the same length, which is 4, and so we enter into our loop, and before we enter into our loop, we initialize results to 0. Okay, and we also check the ASCII character for each element in the A or B. Okay, that is the password and the correct password. Okay, so we check the ASCII character and we do an XOR operation, which is an XOR operation, and then we actually OR it against the result. And in the end, the result, if it's 0, then we return it's true. So what I actually mean by this is, so for example, if say we have again 1089, it's going to run through all of this, the 1089, without stopping. What I mean is this: so it's going to compare 1 and 1, okay, then it's going to update result. It compares 0 and 2, update result, 8 and 3, update result, 9 and 4, update result, then it returns false. So we see that all the 4 characters have been processed. The same thing applies for the 1, 2, 4, 6. So 1 and 1, it updates result, 2 and 2, it updates result, 4 and 3, it updates result. Over here we see that the result is actually going to be 1. Then it's going to compare 6 and 4 again, result is going to be 1, then it returns false. Okay, so that's essentially what we're going to look at. And this code is going to be in the constant time compare.py. Okay, so we have the XOR operation where the XOR operation is this, the caret symbol, and the OR is basically just taking the ASCII character, and then of course I'm going to sleep for 50 milliseconds. Okay, just so we are on the same page. Okay, just like the other one. And yeah, essentially the same thing. That's essentially the pseudocode we just looked at. And so let me try running this code. We also have its script, which is a constant time sh.sh. Okay, it's basically the same shell script, with the difference being that I'm passing in the constant time compare.py. Okay, so it's also going to do the averages and then do the computation. Okay, so we have constant time. Let's print it out first and let's see. Okay, now we see the values, and over here we actually do see that regardless of whether most of the the elements are the same or not. You see that the timing is not so different. That is, we have 233, we have 231. Even for the correct one, we have 233. Wrong ones 232. So they are around the same, the same time, and that's achieving a near constant time, perfection, I should say. Okay, so that's essentially what I wanted to show you guys. And then for this one, I'm going to also plot. I also do have the script here, so please give me a few seconds. We're almost done. It's almost it's constant. That is because the numbers are around 0.233 to 0.237. If we actually zoom out a little, for some reason I don't know how to do that, we actually zoom out, you see that it's going to be constant time. The reason why it's not actually on the same line is because, as I said earlier on, there's compiler optimization. There is also context switching, because I have background apps also opened and all that, and maybe some daemons are already starting and closing and all that, so it's never actually going to be constant. But we see that this one actually achieves a near constant time. Okay, so yeah, that's essentially what I wanted to show you guys. And if you're interested in seeing the scripts, I'm going to place it into my GitHub. I'm going to write it in the description below. And if you do like my content, please like and subscribe. And yeah, thank you guys for watching, and see you in the next video.